Thank you. Alright, so good afternoon everyone. How are you doing? You well? Had a good weekend? Yeah? Enjoying the rains? At least not so hot. Okay. So let's start. Let's continue talking about matchings. Right, so we have talked about a bunch of optimization and decision problems. The one I want to focus on today, which is kind of, in some sense, one of the most fundamental problems, is the following optimization problem. Given a graph G, find a maximum. That's it. Here, maximum matching is a matching of maximum cardinality. There are no costs on the edges. The edges are about cardinality of matching. So this is any matching of maximum cardinality on almost all matching of the graph. Right? For example, if you want to find out decide whether a graph is a perfect matching, right? Well, if you could find a maximum matching, you would just do that. If the cardinality is n by 2, that's a perfect matching. Otherwise, the graph does not have a perfect matching, right? So if you could solve this problem, you can definitely solve the problem of finding or deciding whether the graph is a perfect matching or not, right? Yeah. Good. So this is what I'm going to focus on. And we will need some terminology. We don't need to see any algorithm. We are going to see a very high level algorithm, but there are details which we will figure out much later in the course. Right? So there is going to be an idea, but before that we need some terminology. So let's consider the usual graph where we can draw. So what would be the most naive way to try to find a maximum matching? Like if you had no idea about the difficulty of the problem, what would be the most naive thing you would try to do? Yeah,
enumerate all subset of edges, check if it's enough.
Enumerate all subsets and check if for each subset it is matching or not. Right. But let's say I'm worried about how much time I spend. I mean, I don't want the algorithm to be necessarily correct, but I'm worried about time. So then what would you do? So this you would do if you didn't care at all about time, you had all the time in the world, then you would just do this. And this will work, right? This is going to be, this will give you a correct answer. So what if you were worried about the time you spend?
Keep adding edges.
Keep adding edges, right? That is generally called greedy. Right? So the most natural thing to try would be to go greedy, right? So if you do that here, well, it's greedy. I'll pick this edge, and because it's greedy, it's not looking at anything else. I can now pick any other edge that is not actually set with this edge in order to get a matching. So I could pick this, I could pick this, maybe I'll pick this because it's greedy, right? I mean, I'm not using any additional knowledge. So now what would I do? Now can I pick So I stop. Right? But you all agree that this graph that we have seen multiple times before actually has a larger matching, one of cardinality 3. Right? So greedy would give you this, and now we are stuck. Right? As far as greedy is concerned, can't be any more than this. So, what we will discuss is a concept that can be used to get something better from here, not using greedy. I mean, greedy is stuck. Right? So, we are going to abandon greedy, but we are going to do something slightly different. Okay? So what we will do is we will consider some path in this graph. I'm going to actually make this example bigger. Of course, if I make it bigger, then greedy will again work, but I don't want to do that again. And I've already abandoned greedy. So let me make this example a bit bigger in order to illustrate things more clearly. Something like this. So here is my bigger graph. 6, 7, 8, 9, 10, 26, 0 to 9. I still have the matching, the yellow colored matching that you see. That is 0, 1 and 4, 5. But we have abandoned greedy. Okay. So in order to discuss this other concept, we need some terminology. So let me just do that. And as you can see by now, I'm not a big fan of writing terminology definition. You can write that. I'll just do this through example. So we will look at this matching 0, 1, 4, 5. At every vertex, if you look at the yellow edges, the degree is either 0 or 1, right, by definition of matching, with respect to the yellow edges. If it's 0, we will say that the vertex is exposed. If it's 1, we will say it is saturated. With respect to this matching, so the M exposed vertices and the N saturated vertices. How many saturated ones? 4. 0, 1, 4, and 5. The rest of them are exposed. 2, 3, 6, 7, 8, 9. Yeah? Okay. I like to put a circle, a yellow colored circle around the exposed vertices. Right? So the yellow circle vertices are the M exposed vertices, and M itself is the yellow edges, and those ends are saturated. Okay? Okay. So now what we are going to do is we are going to look at some kind of a path. Some of you have already seen this in your previous courses. If you have seen it, great. If you haven't, better. Right? We are going to look at some kind of a path in this graph, and we are going to use that path to get a better matching. Okay, what's a path? It is exactly what we think it is. A path basically looks like that. Yeah. And if you add one more edge joining these two ends, what you get is a cycle. 3 more cycles later. That's a cycle, that's a path. If you remove an edge from a cycle, you get a path. Formal definition, cycles are connected to regular graph, and a path is cycle minus one edge. The only issue is there are small paths. We will allow this to be a path. Because you are working with simple graphs, this is not a cycle minus one edge. And we'll also allow this to be a path. Single These are not cycles. The smallest cycle, if your graph is simple, is this. Yeah? So these are paths and these are cycles. And for both we will use the notation P or C, I, where I is the number of edges. Length of a path of a cycle is the number of edges. So therefore this is C5. This is C3. This is 1, 2, 3, 4, P4, P1, P0. Yeah. Okay. So what we'll do is we will look at a certain type of path in this graph, and on that path we will do some kind of switching. The word itself says everything you need to know about. On that path we will do switching in order to get a bigger matching. Yeah. So question is, can you find a path in this graph G such that switching on P results in a larger matching? Yeah. I haven't, of course, defined what switching means, but generally we know what switching means. Can I help you find a path like this? Yes.
601458.
601458. Six zero one four five eight. Is that right? That's the path?
Yes.
Okay. Let's put the yellow annotations. 01 is in the matching, 45 is in the matching, 6 is actually exposed, and 8 is exposed. Yeah. What are all these features delimited? The features being the edges are alternating between being in the matching and not being in the matching, and the two ends are exposed. Were they delimited by choice? So not a coincidence. Okay, so look at this path. So can we now use this path to get a better matching? Somebody else, definitely. When we use this path, so what is it we use this path P? Supposing this is a path P, can somebody suggest a way to get a better matching?
601458.
Yeah, what about that?
We just switch the matching.
We switch. Okay, so we throw the ones that are there and we include the ones that are not there. Yeah, Manoj, thank you. Okay, so what we do is we will drop the edges that are there from the matching and include these three edges. This is what we mean by switching. Yeah. So now we have a new matching. Of course, in this case, since both the yellow edges were in the path, now they are both gone. Yeah. Now we have a new matching with three blue edges. Right? So those are now the saturated vertices, and now the exposed vertices are this fellow, this fellow, this fellow, and this fellow. Yeah. So now with respect to n, so let's call this n. N is the new matching. N is 6 0 1 4 and 5 8. Now with respect to n, can somebody find a similar path? This was P. Now can you find a path Q that will result in an even larger matching? Yeah.
So you can go from 6 to 7, 7 to 2, 2 to 1, 1 to 4, 4 to 5, 5 to 8.
Okay. How long is your path?
Length 7.
6 to 7.
Yeah, 7 to 2,
7 to 2.
2 to 1,
6 to 7, 7 to 2. Okay.
2 to 1,
So I'll just write it down. 6, 7, 2,
1,
1,
4,
1,
5,
5,
8,
8,
and then
and
9.
9. Okay. Is that your path? Yeah. Okay. Let's color the things. Let's do the blue annotation. So 6 is actually 6 to 7. Okay, 6 is actually saturated. Now we are doing with respect to blue, right? 6 is saturated. Oh, sorry. It's saturated but not by this edge. It is saturated by another edge from 6 to 0, like this. Yeah? Okay. 7 is actually exposed. 2 is also exposed. 1 is saturated to 4, if I may use that. 4 to 5, okay, 5 is saturated to 8, and 9 is actually exposed. Is that the path you wanted? Or do you want to modify your path?
Like, I thought we were replacing the current path with a different
That's okay.
path.
You can revise your thoughts. Okay. So do you want to go with the same path or do you want to make a slight change in your path? For example, can you take a subpath of what you have suggested? Yeah, you want to take a subpath? Which subpath would you like to take?
We could 7 to 2.
Okay, you want to start at 7?
Yeah, I mean, we could continue from 6, but
So you want to throw away 6?
yeah.
Is this the path you want?
No.
No. Okay, you're almost there. Look at this drawing. How far is it from there? Okay. So shall we go with this or shall we do something else?
I think this what?
Okay, can you make it work? You're quite close. Throw away one more vertex, you're done. Okay,
We can.
go ahead. You're almost there. You just need to throw away one vertex. It's exactly the same length. Just replace yellow by blue, you have what you have, and you throw away one vertex. That's it. Anybody seen what vertex you should throw away? Which one? 7. Throw away 7. Now this is exactly that drawing where blue has become yellow, whatever. Yeah. Now do you agree that we can switch on this? Yeah. Now we can switch here, right? So you can drop the 1, 4, and 5, 8, and I'll pick the alternate edges. Do you see the point? Yeah. Okay. So let's do that. So if you do that, this is actually more interesting because at least you are not using all the n edges. So you are now looking at which paths? We are starting at 2. So we're going to include 2, 1. We're going to drop this fellow. We're going to include 4, 5. We're going to drop this fellow. And we're going to include 8, 9. Did it actually become bigger? Ah, yes. What about 6, 0? We didn't throw it away. So therefore it is still there. Bigger. Yeah? Okay. So the new matching, we have M, N, I'm running out of letters. So I don't know, N star. It's 6, 0, 1, 2, 4, 5, and 8, 9. Yeah, we started with the matching of cardinality 2, we got to 3, we got to 4. Yeah, okay. So in general, if you see a path like this, which we haven't really defined, if the path looks like this, whatever that means, then you can switch and get a bigger matching. Yeah? Okay, so let's define it. So we'll define one more term before we define this. We'll define an M alternating path. Here G is a graph, M is a matching. And the name basically tells you what it is. Right? Can you all guess what it is? The edges of the path should alternate between being in M and not being in M. Yeah? Okay. Any path whose edges. One important point. There are multiple viewpoints for paths and cycles. You can think of a path or a cycle as a subgraph. Subgraph means it has vertices and edges. But you can also just think of paths and cycles as sets of edges. You can't really think of them as sets of vertices. You see the problem? What's the problem with viewing a path or a cycle as a set of vertices? Why can you view it as a set of edges, but not as a set of vertices? Exactly. A set of vertices, you have multiple orders for the same to get different cycles or paths. Right? But a set of edges, if it is a path, it defines a unique path. The ordering is automatically imposed by the set of edges itself. Okay, so therefore a path or a cycle, we will generally view them as sets of edges. But you can also view as set of subgraph. View as a subgraph or maybe both as a set of edges. If you want vertices, you need a sequence of vertices, not just a set. That's the most useless viewpoint, so I will not write it. So, an alternating path. Now, because you have a set of edges, from the set of edges, you automatically get a sequence of edges, if it is actually a path. Right? So therefore, when I say whose edges alternate, I am now referring to the sequence of edges that is defined by that set of edges. There are two sequences, one this way, one that way. Any path whose edges alternate between being in M and not being in M. Yeah? So if you traverse in one direction, doesn't matter which direction, the edges will alternate between being in M and not being in M. Yeah? And I will also use the same terminology for a cycle. If a cycle has the same property, we'll call it an alternating cycle. Okay? So, question. If I have an alternating path, first of all, Can we say anything about the length of an alternating path? Would it be arbitrary or is it somehow going to be more restricted? We have just defined alternating path. Could be anything, right? Could start and end at M, start at M but end not in M, whatever. Anything is possible. Let's just draw some examples. So if my M is yellow, and an alternating path basically looks like this. These are the three types. Yeah?
An empty path considered.
Empty path, good point. Is the empty path an alternating path? Yeah, it is. We will call it an alternating path. And a single edge is always an alternating path. Single edge is always an alternating path. Empty path is always an alternating path because the condition is clearly satisfied. Yeah? Of course, generally speaking, the empty path is pretty useless. But yes, as far as definitions are concerned, I allow the single vertex to be path. Okay. So, will any alternating path help us in getting a bigger matching, or do we need some additional properties? So now let's go back to what we did. First, we took this fellow with respect to the yellow matching, and we got a bigger matching by doing this switching business. Then we went to this path, right, which is blue alternating, and we did switching and it worked. We got a bigger matching. So, what do we need to get a bigger matching? Is alternating path enough, or do we need some additional conditions? What are the additional conditions? Can I see your show max? Yeah. Yeah.
Just after the report.
Sorry.
Last
The two outside vertices have to be exposed with respect to the matching.
Yeah.
Yeah. Good. Thank you. And you are?
Sriram.
Sriram. Thank you. It's your first lecture?
Yeah.
Okay. Right. So, yeah, so we want the ends, these two fellows. Observe that these two fellows are n exposed. And here observe that these two fellows are n exposed. Yeah? So if we have a path with this property, we'll call it an augmenting path. And there is one small problem. Can you tell me what that is? Right. This is the only issue. I don't want this to be an augmenting path. This is useless. Single exposed vertex cannot help me getting a bigger matching. Right? So we are going to restrict the path in this case to not be a single vertex. We are going to have two distinct M exposed vertices as the ends of the path, and we want it to be alternating. By the way, I didn't define, but clearly I have been calling these the ends of the path. A cycle clearly does not have ends, or rather every vertex is an end. Okay. So, an end augmenting path is any M alternating path that has distinct M exposed vertices. That is distinct M exposed ends. That's it. Yeah. Questions, concerns? Everybody is happy with this? So now we have this large matching N star with 4 edges. Can somebody give me a very straightforward n star augmenting path in this graph? Like really straightforward. I want a pink augmenting path in this graph. Yeah, what is it?
7, 6.
No, more straightforward. You might be right, but I want more straightforward. I mean, I'm trying to tackle a corner case here. Nishad?
7 to 1, 4, 3.
No, straightforward. Too straightforward. You guys?
3, 0, 6, 9.
No, straightforward. Very straightforward. As I said, I'm trying to tackle a corner case here. Yeah,
Just 3, 0.
3-0.
Okay, no.
Pink with respect to the pink matchup. Oh, wait. Oh, sorry. Ah, my bad. Okay, no. So, everybody I said you're wrong, you're all right. I'm wrong. I'm looking at blue and thinking pink. Yeah. So, in my mind, I'm thinking blue and I'm asking you for pink. Anyways. So, what was the first one?
6, 0, 1.
7,
6,
7, 6,
0, 2, 1.
0, 2,
1, 4, 5.
1, 4.
5, 8, 9.
Wow, that's very long. Okay.
8, 9,
3. Is this right? Yeah? I'm not going to check. It's not straightforward enough. But yeah. Yeah. So, good. Everybody agrees this is an augmenting path? And if you switch on this path, what do you get? A larger matching. And in this example, it happens to be perfect matching. Okay. Fine. Good. So now coming back to the straightforward example I wanted, for which I need a straightforward class. I don't know. Can you now give me a straightforward augmenting path?
1, 4.
1. Do you all agree? This is an augmenting path where n was the original 2 edges. Yeah. So that is the case where you have a single edge, both ends are exposed. You can just throw that into the matching and you're done. Yeah, that's basically VDD. Okay, so good. So what's the main thing you're doing? Let's try to formalize things. So the observation that we made is G is a graph. G is a graph. N is a matching. And that's a P is an n augmenting path what can you say about the length of an augmenting path? Yeah, everybody agrees? An augmenting path, unlike an alternating path, always has odd length. Then can somebody tell me what is the larger matching? Right, in each case, you were able to do something and get a larger matching. So can somebody, maybe you all can try, see if you can write down the definition of n, such that n is a matching and the cardinality of n is the cardinality of m plus 1. Write down the definition of n. EIN, do it now, right? Is that right, Lulu? Do it now.
Such thing is baked into the definition of P itself or?
Sorry.
So we are defining P such
Yes, P is given, M is given, P is given. I want you to define N. N should be a matching, and its cardinality should be exactly one more than M's cardinality. I just want you to formally define it, which we have been doing all the time. I want you to write a short definition of N. I give you a hint for that. Use set theoretic concepts, operations, notation. Those who have written N equal to P minus M or something like this. Apply your point to N to N star. How did he go from N to N star? And observe that it doesn't work. Yeah.
But then the pathway was not an augmented pathway.
No, it was augmenting. When we went to N, from N to N star, we took this path, which is a blue augmenting path. But the operation we did is not that straightforward. It is slightly, I mean, there's a very simple way to make it correct, but yeah, there is no way to do it. If your path is spanning all the vertices, then what you are saying is correct. If your path does not span all the vertices, then this doesn't work. What I said is not even obvious. Yeah, I can make it even obvious. It will not obvious. If it is spanning all the M saturated vertices, then this is correct. If it is not spanning all the M saturated vertices, then it is. So you want to switch on the path, but only on the path. Outside the path, you want to keep things as they are. You don't want to disturb things outside the path. Right? If you lose those edges, then you may. Yeah? Okay? Yeah. Right? Does everybody see what to do? Yeah, you see how to fix it?
Minus P, ODM P minus.
And that is also called symmetric difference. Yeah. So, yeah. I shall use this for symmetric difference. Okay? This is the symmetric difference of two sets. Right? When diagram wise, it's basically this one. Yeah? So if you take the symmetric difference on an augmenting class, what you have is indeed a bigger matching, bigger by exactly 1. Good. So now let's go back to our original optimization problem. We want to find the maximum matching. So if you have a matching M, if you are able to find an augmenting path, then you would simply augment or switch on that path and get a bigger matching. Right? And if you can find one, again do the same thing. Now with respect to the new matching, find an augmenting path, get a bigger matching. Of course, what is not clear is why this works. Like why should this actually give you a largest matching? Right? So if you want to prove, so let's write down an algorithm at a high level. So my input is simply a graph G. And the goal is to find maximum matching. So one way to do it, or one way to try with this new idea, observe that this new idea helps us at least getting over the greedy limitation, right? At least you can make examples where the greedy one will not work. The very first example we made, the greedy one will not work, but the new idea will actually work. In fact, that is probably true. That is true for the pink matching. If you look at the pink matching, then I was looking for a very straightforward augmenting path, but we all realized eventually, or rather I realized that it doesn't exist. So from the pink matching of cardinality 4, there was no way to go to a matching of cardinality 5 using the greedy method. But there is a non-augmenting path, or there is a non-trivial augmenting path, and using that path we were able to get to a larger matching. I did not draw it, but I guess you all can draw it. Okay. So therefore, this is better than greedy. Is it good enough? I don't know. So here is the algorithm. Start with the empty matching. And find an augmenting path. Until you are able to find one, keep augmenting the matching and keep repeating. Right? So until there exists an n augmenting path, find such a path, or I'll just put that here. Until there exists an augmenting path, keep doing the following. Take the current matching and replace it by the symmetric difference of the current matching with the path P, where we view both as edge sets. Matching is anyway a set of edges. Here I am also doing the path as a set of edges. Yeah. If you are worried about whether the TA or me would understand your viewpoint, you can make it clear. Yeah. So then it's clear that this is an answer. Or you can just let it go. Keep doing this. Return n. Right? Is that how people write pseudocode these days? Yeah, is that okay? Suitable? No, it's not. It's but it seems to work.
So isn't it until that does not exist?
Sorry?
Until that does not exist?
Until that does not exist, yes. Sorry. Until there exists an unlimited path, keep doing this, so I do this. If there exists an unlimited path, do this. Okay, fine. So I guess it depends. Okay. Let me just remove until it's confusing. If there exists an unlimited path, do the following, right? Else you break out of this thing. So maybe what's the right way to do it? I want this to be repeated. I can use go to, right? Who else? This is not the coding class. I can use go to. Yeah, I thought do it in actually compiler classes and all that. Don't tell them I go to use go to. I remember once upon a time when I did these things, they were like, you are going to use go to. You get the point? So if there is a protein path, augment, go back here, and when this condition is not true, you will leave. Yeah? Okay. So that works. Yeah? Does it actually work? That's the problem, right? Does it actually find the maximum matching? Or is it trivial that it definitely will find a maximum? Is it trivial that it should find a maximum matching? Supposing it does work, what do you need to prove?
If you have
What is the argument? Is that? Supposing you think it works, what do you need to prove that it actually works? Okay.
Yeah, so if we have a maximum matching, we should not have an augmenting. And vice versa. Like if
Can you tell me the whole if statement?
the graph has an augmenting path, if and only if m is not the maximum.
Okay. That's it, right? G has an n augmenting path. If and only if there exists m is not a maximum match. Yeah? Supposing this is true, supposing this is a true statement, then do you all agree that this works? Like we are not about efficiency, and I am not talking about how to implement the subroutines. But supposing, yeah, so here the assumption is that there exists an accounting path, and I am able to find it because I am using it in the next step to do something interesting, right? So, supposing I can do all these things in polytime, and supposing this statement is true, then you all agree that this is going to be a correct algorithm that will find a maximum matching, that will return a maximum matching given any input graph. Yeah? Okay. So let's look at this statement. One direction is easy. We have already proved it, or we have already observed it. Can folks figure out which direction we have already observed? Maybe raise hands. Which direction we have already observed? Same hands for this. Many hands. Okay. Forward is already done, right? Forward is done. If there exists an augmenting path, then we were able to augment and get a larger matching, therefore it is not a maximum matching. So forward is done. Yeah, that's exactly this. Forward is done. Reverse is true or not? What does the reverse say? Reverse says that if it is not a maximum matching, then there is an augmenting path. If a given matching is not maximum, then there exists an augmenting path. Is that true? Well, some of you may know where this appears. It appears on? Sorry? True. But it also appears on your assignment problem. So you do it assignment. parts for you and then ask you to do it. So it will be rather straightforward. Good. So this is actually a result by Berge. Berge is Lemma. Not very difficult to do, as you will find out on the assignment. This is Berge's Lemma. Okay. So therefore, this is a correct algorithm. In the sense that if you can actually find augmenting paths in a reasonable amount of time, then it will also terminate in a reasonable amount of time. Okay. So, the hardest part here is how do you decide this? Deciding whether there exists an augmenting path. Decide whether there exists an augmenting path. Or equivalently, well, even better, actually the decision is not enough. I don't want you to just say yes or no, right? I want you to give the path. Maybe it's better. Maybe that's what we really need, because we are using the path in the next step. Or rather, what we really need is a way to find an augmenting path when it exists, or give a certificate for its inexistence, or conclude inexistence. How do you conclude? In life, anything, using a certificate, right? So, if you can do this efficiently, which means polytime, deterministic Turing machine, blah blah blah, then what you have here is a polynomial time algorithm to find a maximum. Right? Because anyways the loop or the go-to cannot run too many times, because cardinality of maximum matching is anyways bounded by number n by 2, right? You will see that. Okay. So anyways the go-to statement cannot run too many times. So all you need to do is you need to find a polynomial time algorithm for this subroutine. The subroutine will just tell you here's an augmenting path, or it will give you a definitive certificate that it does not exist. Yeah? And this is not easy. This is hard. For bipartite graphs, the Hungarians and others have figured out how to do it back in the 1930s and so on. For general, that means non-bipartite graphs, it was Edmonds 1965 who figured it out. Right? So, bipartite easy, relatively, it's not trivial by any means, but in the grand scheme of things, it is straightforward. General, in general, Edmonds 1965. And we will see these in module 4 most likely. But I just wanted to give you almost any algorithm, any implementation out there that finds or that promises to find the maximum matching basically uses this. It basically needs to find an augmenting path while it exists. That's pretty much what every algorithm out there is based on. The hard part is just this subroutine. Questions, concerns? All good? And let's go back to our point. If we can solve this optimization problem, we can also decide whether a graph has a perfect matching. Right? Because when a graph has a perfect matching, maximum matchings are precisely perfect matchings. There is no difference between the two concepts. Right? So therefore, if you want to find a minimum cost perfect matching, then again you need to figure out whether the perfect matching is there or not. So even when we go back to our cost version of the optimization problem, minimum cost perfect matching, we will need something like this to figure out whether the graph has a perfect matching. Okay. So, are there any questions, concerns regarding any of these things? All good? Okay, if all good, we will take a short break and then we will start talking about the next problem, shortest paths. And good news is we already talked about what a path is. So we take a break. Yeah? Thank you.